Okay, good morning everybody. Can everybody hear me at the back, yeah? If not, I can shout even louder. So thanks for the introduction, Fraser. You guessed from my accent that although I'm currently based at Northwestern, I'm actually Scottish, and I used to be at the University of St Andrews, and I still actually retain a small group there. Okay, so what I'm going to talk to you today is about systems. And systems really are all around us, from the very largest scale to the very smallest scale. And we tend to associate systems with certain properties. So at the very largest scale, you might associate traits with populations. This is really just an excuse for me to show a really nice picture of Glasgow, which is where I'm from. But in Glasgow, there is this very large building that has a very large poster on it that says, "People make Glasgow." And I think if you go to the UK, there are certain traits that are associated with people from Glasgow. One of them is probably being loud. Another one's possibly the sort of love of deep-fried food. But also, people from Glasgow are associated with being very interactive, okay? Now, interactions are really important in the world around us. For example, the weather systems, the stock market, all over everything we see, interactions drive what is going on. Now, I really like this quote from the late Douglas Adams, which basically says that the world has inordinate complexity. It's rich, it's strange, it's amazing. But the critical thing is that this complexity came out of simplicity. In fact, it might have come from nothing at all. And the question is, how does this happen? How do you get complexity from something simple, or indeed nothing at all? Now, some things are very simple. A two-body problem in physics has a steady state, it's a stable outcome where these two bodies will simply orbit each other happily for eons. As soon as you introduce a third body into the system, but with the same total angular momentum in the system, it's chaos.
They want you to wear the mic.
Wear this, two mics.
Now they'll be able to hear you. You can slip this into your own.
Okay. You all said you could hear me. Means I don't have to shout. So with three bodies, this gets very chaotic very quickly. So the question I'm going to spend the next sort of 17 minutes addressing is, where does simple stop and where does complex start? And for me, that's what systems chemistry is. Trying to transition from chemical systems that are predictable to ones that behave like an ensemble. So in essence, what I'm going to propose is that we need to think a little bit differently about the origin of life. We tend to be very focused about biomimetic or biorelevant molecules. And we need to think carefully about what we think information is and what a genotype is. So I just want to show you very briefly just a simple thought experiment that will illustrate what I mean. So let's imagine we have these two chemical reactions. They operate completely independent of each other. They have different reagents and different products. As a network diagram, we can look at it like this. There's no connection between the top and the bottom. And what we have is essentially two products completely independent of each other. Let's now introduce just two connections in that system. So now, for example, A, which originally reacted with B, can also react with C. This is really simple, right? It's a really simple network. And yet, if we look at what the output is, it depends on, for example, AB depends on this rate law, But this rate law now has terms in it for all 4 of the reagents, not just A and not just B, but all 4 of them. And the result is that if we monkey around with these rate constants that determine how fast those reactions will go, as the rate constant for the formation of AB increases, so 2 and then 10, you'll see that a pattern emerges here. We did not do anything to this reaction here that makes CD, right? I didn't change that rate constant, and yet this product is upregulated by this network. Okay, and this is an illustration. I'm going to show you an example, a real example of this in a minute. But what we're saying essentially is we need an instruction, make this reaction go faster, and if we have the right connectivity, that instruction can bring about a system-level propagation of that information. So essentially what I'm saying is systems chemistry is not like this chemistry, which is reagent, product, and a single path. It's more like this. There are people in the audience who will recognize where this is. If you've ever been to Birmingham in England, this is the Gravelly Hill multi-level interchange. Famed for people getting lost on it. Actually, to navigate this, all you need is a set of instructions. You need to be told to go down one path rather than the other path, and then you can reach the multiple exit points of the system. Now for us, an instruction comes from replication. We've been interested in replication processes for probably more than 15 years. I'm just going to run you through very quickly how you make a molecule copy itself. Okay, we're probably all familiar with the idea of nucleic acids copying themselves. I'm going to abstract this, and I'm going to show you some completely chemical systems, completely synthetic systems, sorry, that will replicate themselves. So the idea is very simple. You have something that forms a bond, this is in red and yellow, and something that can recognize itself in green and blue. So if you join A and B together, you get this guy here. Now normally that reaction, in the absence of any recognition, will be slow, it will be unselected, because you're just relying on random collision. Once you get recognition involved, of course, there are 2 different pathways. This blue bit can recognize the green bit and assemble a binary complex, and that binary complex can react. For us, that's quite uninteresting because the recognition that you used to assemble the starting materials lives on in the product. Much more interesting is if you engineer this gray bit to hold the 2 recognition sites far apart from each other. What you can then form is a ternary complex, which assembles A and B. It controls the approach of A to B, and therefore the reaction between them. But what you've done is make an exact copy of whatever T is. You have replicated T. If you then dissociate that dimer, you return one template to the start of the reaction, and you generate another one. So 1 will give 2, 2 will give 4, 4 will give 8, and so on. Now actually, the exponential growth here is not important for what I have to say. What is important is to realize that adding template is an instruction. It says, make me, and its effect on the process is to increase the initial rate of reaction. So I want you to get the idea that adding a replicating template is just an instruction. It says, make this. Okay, so just to give you a flavor of the molecules that we use, and actually through the rest of what I have to say, the chemical details are not super important. The recognition is driven by hydrogen bonding between an imidopyridine and a carboxylic acid. As we go through, you'll see some structures. There are various appendages on this ring. These are functionally not very important. They just change things in the details. We have this kind of weird-looking way of joining molecules together. And we chose this for 2 reasons. One, the reaction is really hard to accelerate in any other way than via replication. And secondly, we use the ratio of these 2 products as a marker for replication. This red one, where this group and these 2 protons are on the same side of the bicyclic ring, this is the one that generally replicates. In the absence of any replication, pretty much metronomically, this ratio will be 3:1. Everything I'll show you, I think, pretty much has this to this at somewhere about 50 to 70:1. Okay, so we've done lots of things with replication. We've generated patterns, we've made rataxanes, we've made propagating waves. What I'm going to focus on for the next, well, for the rest of my talk, in fact, is thinking about some 3 key properties that are required to make a functioning system that uses replicators and a replicator network to encode its genotype. So in other words, to encode what its outputs will be. So the first of those is the idea of a genotype being persistent. Okay, we're kind of, I guess, comfortable with the idea of biological genes being persistent. But what about replicator networks? Can you encode within the reactions in a network a genotype that is persistent? Now, in order to help you understand this, I'm going to have to show you another way of making a molecule replicate itself. And this is a reciprocal model of replication. So what I showed you previously was a template copying itself. I'm going to show you a template that makes a complementary partner, and the complementary partner makes the original template, which is much more like the way DNA functions. So here we have a yellow replicator and a gray replicator. The gray replicator picks up the yellow bits and joins them together. We dissociate that duplex. The yellow replicator picks up the gray bits, joins them together, and we complete 2 interlocked cross-catalytic cycles now. Okay, so how do we make a system out of these building blocks? So here's one self-replicator. So this guy copies itself, and it copies itself because it has an imidopyridine and a carboxylic acid. So those are complementary. That template is self-complementary, and so it will guide its own formation. This guy will do the same thing. Here's the carboxylic acid, here's the imidopyridine. Now, on the board, we have 4 reagents, and you combine them in a particular way to make 2 self-replicators. Now, if you think back to that little network I showed you right at the back at the start, it had 4 reagents. This has 4 reagents, and we can combine them in another way. We can add this to this and this to this. And what we get if we do that are 2 reciprocal templates. So from only 4 reagents, we can get 2 self-replicators that make themselves and a pair of templates that make each other. So if we want to look at that in terms of catalytic cycles, this is what it looks like. You have an autocatalytic cycle that makes, where the light blue template makes itself, the dark blue template makes itself, and pink makes red, and red makes pink. All from just 4 reagents. So what happens here? Well, we do a lot of physical organic chemistry, and I just put this slide up just to emphasize the fact that we measure kinetics of just about everything we look at. So we're trying to get a deep understanding of what happens in this system. But if we take a sort of 20,000 foot view, this is what happens. If you just mix A, B, C, and D, and you just let them react, you'll get a ratio of reciprocal replicators to self-replicators of about 2:1. So it appears that the reciprocal replicators are a bit more efficient than the self-replicators. But what's important is that this network responds to instructions. So here's just a bar chart of the kind of final output. So here, in red, the reciprocal ones, in blue, the self-replicators. If we add a reciprocal replicator, just one of the 2 reciprocal replicators, both of them are upregulated and the 2 self-replicators are downregulated. If we add just one of the self-replicators, both of the self-replicators are upregulated and both the reciprocal ones are downregulated. So although the instruction was, for example, make T1, because of the connectivity of the system, because of the chemical genotype of the network, we'll actually end up upregulating both of them. And this works with either of them. You can add T1 or T2 and you see the same effect. So then you can start to ask the question, right, the system starts off in a position where it's biased towards reciprocal replicators. What if we did a serial transfer experiment? So if we want a sort of color analogy, it starts off red because it favors the reciprocal replicators. So if we do a serial transfer experiment and use the output of one reaction as the input of the next, do we amplify that? Well, if you just take the reaction, it becomes biased towards reciprocal replicators, and then you take some of that out, add it to new feedstock, do a second reaction, and so on and so on. You'll see that very quickly we sort of reach a plateau in terms of composition. Now you might say, well, you weren't really instructing the system there. You were just kind of saying, well, do what you like. So let's give it a specific instruction. Let's start off with fresh feedstock, add template, and this time we're either going to add a reciprocal replicator or a self-replicator. Now you can see if we add a reciprocal replicator, yeah, the amount of reciprocal replicator to self-replicator jumps up from that 2 to 1 to about 3.7 to 1. So yeah, absolutely, we've biased this system more towards reciprocal replicators. But as we do this, serial transfer experiment, you can see that this comes back. If we bias it towards self-replicators, it comes back. Now, it's easier to understand just by plotting what's going on here, just as points represent the ratios in each serial transfer experiment. What I want you to get from this is that no matter what you do, and we have lots more experiments in this system always comes back to a fixed ratio. Now, you can trace that through analyzing the kinetics and show that it's a function of the network connectivity and the kinetic properties of each replicator, and it will always come back to a given steady state. In other words, that network, although you can push it one way, you can push it another way, it will always recover and it will always end up in the same place. In other words, the network is persistent. So persistence is one thing that we get in biological systems. The next thing is kind of metabolism, being able to turn over feedstock. So we do this using a dynamic library and exploiting Le Chatelier's principle. So imagine we have a bunch of reagents that can all exchange with each other, and then we transfer material out of that pool in an irreversible way. And we're going to do this with a replicator. So stuff that's out here can't get back in here. But anything that's in here can exchange with anything else in here. So what we're going to do is we're going to use an instruction to say make big D, and that instruction is going to be a replicator. So let's start with these two reagents at the top here, and then what we're going to do is we're going to have some exchange, and we're going to have this guy as a replicator process this exchange pool, pull out this component, react it with this one, and generate this. I'll just point out from a chemical standpoint, this is a bit of a bonkers reaction, because when we start this reaction, in solution, there is none of the compounds required to make the replicator. We're actually going to synthesize those compounds using the network. So at a very high level, here's where we start in the reagent pool. We have two reagents, and you see these get processed into a set of different reagents, and then we take one out and we amplify it through replication. If we actually give the system an instruction, in other words, we add some of that replicator at the start, we should improve this situation, and indeed we do. That's a kind of one-trick pony. That's one replicator. What about replicators competing with themselves? Well, you can do this equally well. In fact, you can go completely nuts. You can just give the system a big pool of stuff and say, hey guys, you sort it out. So this collection of compounds will make 5 nitrones and 20 imines by condensation. you can add a maleimide and you can get 2 replicators out of this. Now, if you look at what happens here, this system, if you don't add any instruction, will make about twice as much 4T as you do 3T. But if you add an instruction 3T, or add an instruction in the form of the replicator 3T, you'll upregulate this guy. And if you add 4T, you'll upregulate 4T. And the system responds in a particular way. But remember, these replicators are affecting that dynamic pool. And what I'd say is it's a sort of model of metabolism. It's making the compounds that it needs in order to assemble itself. Okay, so that's metabolism. Other things that you're going to need are remote influence. I've shown you direct influence, where a replicator makes itself or it makes its partner. But what about remote influence? Many enzymatic pathways have feedback loops that stretch right across the length of the pathway. So can we do that? So here's an idea of where we've begun to think about that. So what we're going to do is we're going to make a replicator, and that's going to be autocatalytic. And then we're going to react that replicator with another species, and that's going to be autocatalytic. But this second replicator, R2, is going to feed back on the first step. So it will influence not only itself, it will influence a remote step in the synthesis. So very quickly, how do we do this? Well, we start with an imidopyridine and a carboxylic acid, and the first, they're the recognition sites, and the first reaction is a condensation reaction to make a nitrone that we saw was a component of a replicator earlier. Now we have two recognition sites, but we're going to ignore one of them and focus on the nitrone. We're going to add a maleimide, which has the other recognition site that we need, and the reactive site, and that's going to make R2. So, phenomenologically, what happens here? So if we take A and B to make R1, we get a typical profile for a replicator. If we add R1, we can see the rate increases. So, okay, we have some kind of a positive feedback from autocatalysis. If we take R1 and the other maleimide to make R2, you see this is a bit slower. You add the template, it gets faster, so we have autocatalytic feedback. Now you can take A plus B, so you're making R1, but you can add R2 to this. And it actually turns out that R2 is a better catalyst for making R1 than R1 is for making itself. So what we have here is actually quite strong cross-catalytic positive feedback across the length of this cascade process. And then you can simply toss everything in together, and the system will quite happily process its way through. If you add R2 to this, you'll actually see not particularly a change in the production of R1, but certainly R2 is upregulated. So overall, we created a system that now has autocatalytic steps within itself and cross-catalytic feedback. Of course, this molecule here has 3 recognition sites, so it has multiple reading frames for that recognition, of which we've exploited 2. You could, of course, exploit the third and get it to interact further downstream with another reciprocal replicator, and therefore build up more complex networks. Okay, Fraser stood up, so that means I need to shut up. I'm going to summarize what I've told you. Networks of reagents and replication events are essential if you want to generate system-level behavior that's based on kinetic selection processes. You can manipulate these networks by instructional templates. Those interactions between the templates encoded a chemical genotype in which, in certain circumstances, this genotype can be persistent. And you've seen also that these networks can process or metabolize just pools of reagents in order to make themselves. Right, finally, I'd like to thank Fraser for giving me a home. Peggy and Stephanie, who I'm not sure are here at the moment, but help run the lab, everybody in the Stoddart group, and particularly these people here, Tamara, Lorenzo, Craig, James, Jake, and Bailey, and David, who's back in St Andrews now, but was in Northwestern for a bit, for all their efforts in making this happen. Finally, thank you for listening.
All right, so off we go with questions, please. Yes. How much additional functionality beyond replication can you build into these systems? You're behind the board. Sorry about that. So this is an amazing way to make a lot of material fairly efficiently. What else can it do? What else can you
So we've certainly made supramolecular polymers that can replicate themselves. We've also had some flirtation with other structure phases like gels. But in principle, it is a kind of a toolbox. You know, you can use these replicating templates to process reagent pools. And really, the limit is kind of your imagination. I think we're starting to think much more about these templates as basically exactly what I just described, just a toolbox. You can append them to something and use this kind of autocatalytic amplification or cross-catalytic amplification to pull one thing out of the mixture rather than something else out of the mixture.
Can we build more capable molecular machines at scale using this kind of technique?
I'd like to think so. I mean, we've kind of dabbled with making retaxanes. We're kind of a prototypical machine. We've kind of dabbled with that. That turns out to be more tricky to do selectively. I mean, we understand why that is. It's just implementing the fix is kind of more challenging. But in principle, yeah.
Thank you very much.
Just from a molecular engineering perspective, we have feedback to a network. We can run into conditions where feedback oscillations. Is there an analogy?
Well, actually it's something we're trying to do because ultimately we'd like to make a system that operates autonomously. So the very simple analogy would be the sort of predator-prey model, the Lotka-Volterra model, right? Which is the rabbits eat the grass and the foxes eat the rabbits, and so you get population oscillations. Now, you won't be able to do that with these systems in a well-stored batch reactor because essentially it'll just get damped out as you run out. But if you put that in flow, which is one of the things we're doing here, then hopefully you can set off one of these kind of oscillations. And you can influence that then by intercepting it by specific templates.
Any more questions?